briefly, let's say that here's our x equals 0 position for this wave, and here's our x equals 4.9 meter position. Okay, there's a delay of a certain number of seconds for 4.9 meters. It's going to be about 1/30th of a second for the wave to get from here to here. And during that 1/30th of a second, this particle is going to continue its simple harmonic motion, so it's going to be ahead of the simple harmonic motion of this particle, which doesn't start until the wave gets here. So that this part is going to be out of phase with this part, unless 4.9 meters happens to be a whole number of wavelengths. Now you can think about that, but just think again about the fact that this motion here is not synchronized with this motion. This motion delays this and is somewhat out of phase with it. Now, picking up on the idea of omega and k here, we can write our equation as A times the sine of quantity omega t minus kx. Incidentally, sometimes that could be written kx minus omega t. You'd have the same effect. It would just, you'd have a little different phase relationship at the beginning. Omega is 2 pi times the frequency. Frequency could then be omega divided by 2 pi radians, of course. The wavelength is 2 pi over k. And you can reason that out simply enough here. Where did that 5 pi radians per meter come from? And if you go back and see how that arose, you can get the connection. But if we divide the 2 pi radians for a complete cycle by the 5 pi radians that correspond to a meter, we're going to get 2/5 of a meter. So there's a simple example of how that would work out. Also, the wave propagation velocity is omega over k. Now, this function can easily be shown to satisfy the wave equation with c equals omega over k. Take two derivatives, you're going to get an omega squared out of each t derivative. You're going to get a k squared out of each x derivative. If you divide the second t derivative by the second x derivative, you're going to have omega squared over k squared. And when you take the square root of that, you get the speed of propagation, omega over k. Now, you're going to have to work that out by working through these signed problems and so forth, but that's an overview of the mathematics of the situation. And again, the wave propagates because of the progressive translation of the disturbance, of the wave disturbance, due to the way the t is replaced by t minus x over 140 meters per second, and that gives you the 140 meter per second propagation in a way that we talked about previously.